In this segment, let's dwell a little more deeper into the Internet architecture and functionalities. What we will see here is the goals of the Internet architecture, an end-to-end argument concerning the same, and again, look a little deeper into the layered architecture of the Internet in terms of what functionalities are there for each layers. Now, let's look at the first part. What are the goals for the Internet architecture based on the discussions that we've had so far? We know that the Internet should support multiple types of services. So there should be support for applications that have different requirements in terms of reliability or speed, latency, etc. It should also support different types of services such as multimedia services, plain web browsing, audio services, file transfer, etc. Internet must support a variety of networks, must enable the interconnection or interworking of different types of networks. A 3G network could be made to work with WLAN network. An ATM network could be made to work with an IP network, and so on. It should allow for distributed management and also be cost effective at the same time. Why all of this becomes challenging is because different networks have different capabilities. Different networks have different characteristics. So they may differ in terms of the address formats. They may differ in terms of performance requirements, bandwidth, latency, etc. They may differ in terms of the packet sizes supported by the networks. The loss rate or the handling of losses may be different, and the routing techniques used may be different also within each of these networks. And it becomes challenging to make these different types of network interwork with each other. With that information, what could be the design goals of the Internet, right? So what are the design goals that we have for the Internet? One is that the Internet communication must continue despite loss of networks or gateways, which means that it should be survivable. It should stand up to any loss of networks. Any router goes down or any link in the Internet goes down, the communication must still continue. There must be a way for the communication to continue. The Internet must support multiple types of communication service. It must accommodate a variety of networks. It must allow distributed management of its resources. Doing all of this at the same time, it should also be cost effective, and it must be scalable in the sense that we should be able to add new hosts or new networks without much difficulties. And the last goal is that the resources used in the Internet must be accountable, which means that we should be able to know how much bandwidth each host is consumed, how many packets has each host been able to send or receive, or how many errors were introduced into the network, how many erroneous packets were introduced into the network, and so on, right? So every transaction or every packet that has gone in the Internet, every single iota of bandwidth that's consumed must be accountable. Now, if you look at these goals are from the ARPANET, and the context of these goals was that the ARPANET or ARPANET was designed to operate in a military environment, right? So if you look at the order here, the first goal is survivability. And now these goals are stated in their order of importance as relevant to ARPANET. If the order were changed, we might end up with a completely different network architecture. So let's just look at these goals as a set of priorities which influenced the design decisions within the Internet architecture. Now let's look at the layered architecture of the Internet again. We mentioned that the network functionalities in the Internet are divided into layers, and each layer implements a certain set of functionalities. For example, reliable or sequence delivery is given by one layer. Addressing and routing is provided as a service by another layer. Security is implemented in multiple layers. Collision detection at Ethernet is implemented by one layer, and real-time guarantees are provided by yet another layer, right? So these are a set of examples of functionalities, and we see that each of them are implemented by different layers. Now, if we were to implement each of these in different layers, where should we place the functionalities or these functions among the different modules of a distributed system? So, should we place them at the edges, or should we place them inside the end hosts? The end-to-end argument says that functions placed at the low levels of a system may be redundant or of less value when compared with the cost of providing them at that low level. Now, what does that mean? Right, let's take an example of a file transfer application. Now, let's take a look at the functionality and the process involved in transferring a file, a simple FTP application, transferring a file from host 1 to host 2. At host 1, the file may be residing on multiple tracks in the disk. The file transfer program at host 1 invokes the file system to read the file from the disk. The file system passes whatever is read into the file transfer program in fixed size blocks. And at host 1, the file transfer program asks the data communication system to transmit the file using some communication protocol to host 2, and this may involve splitting the data into packets. The packet size is typically different from the file block size and the disk track size. Now, the data communication network moves the packets from host 1 to host 2. At host 2, once it receives the packets, the data communication program removes the packets from the protocol and hands over the data contained onto the second part of the file transfer application, and that part operates within the host 2. At a very basic level, these are the various steps in transferring a file from host 1 to host 2. Now, in doing this, what are the threats that we can encounter in each of these steps? Let's look at the hardware faults, for example, in the disk storage system in host 1. Right? The software or the file system, the file transfer program, or the data communication system might make a mistake in buffering or copying the data of the file. There may be transient errors in the hardware processor or local memory while doing the buffering and copying. This could happen either at host 1 or at host 2. The communication system might drop or change the bits in a packet. The host itself may crash during the transfer, right? So there are multiple threats that can happen in each of these steps. Now, how to solve these threats? What can we do to solve or mitigate these threats? One way to do it is to implement each of these functionality and error checks everywhere using duplicate copies, timeout, and retry, and maybe other mechanisms. So when we implement each functionality, each error check, and every single functionality and error check in every single place that is there, it becomes not a very efficient mechanism, especially if we assume that all these threats are relatively low in probability, which means we are designing for the worst case, and the worst case probability is very less. So we are kind of over designing. The probability of these errors happening may also be low enough that the system allows useful work to be done, or work to be accomplished, even if these checks are not in place. So brute force countermeasures, such as doing everything 3 times, might appear a little uneconomical, right? So the other possibility of solving these threats or mitigating these threats is to do an end-to-end check and retry. For example, let's say to correct hardware faults, which is one of the many faults that we saw earlier can happen during the file transfer. To correct hardware faults, we store each file with a checksum that helps detect these errors. The application program transfers the file from host 1 to host 2. The file transfer program in host 2 reads the transferred file back from its disk storage system and copies it into its own memory. It recalculates the checksum and sends this value back to host 1. Now, the host 1 calculated checksum from host 2 with what it had originally calculated. If the comparison fails, then host 1 concludes that something went wrong and a retry from the beginning could be attempted. Right? The efficiency of this method depends on the rate of failure of the file transfer. So if it so happens that the communication system or the hardware faults or whatever the errors are, it happens with very high frequency, then this end-to-end retransmission might happen very often, and that might be inefficient. So this kind of end-to-end solution may be needed not just for FTP but for other applications as well. So now, as a common solution, can the underlying communication system provide this solution? Yes, it can do that. The communication systems can provide redundancy by, for example, checksums, sequence number checking, internal retry mechanisms, and so on. However, the question is whether or not this solution, if provided by the underlying communication system, is actually useful to, or whether it is actually required by the file transfer application. So how do we make a choice here? Let's look at the other threats also. They also need to be eliminated, and to do that, the file transfer program anyway needs to provide its own retry mechanisms based on an end-to-end checksum of the file. And if the file transfer program application does it, then the extra effort by the communication system to provide a guarantee of reliable data transmission may not be really required, may not be really adding much value, because the correct file transmission is anyway assured by the end-to-end checksum and retry mechanism that is implemented by the application, whether or not the data transmission system is reliable, right? Therefore, the argument goes that in order to achieve file transfer, the application program that performs the transfer must supply a file transfer specific end-to-end reliability guarantee. In this case, a checksum to detect failures and to retry if required. For the data communication system to go out of its way to provide these kind of reliability does not in any way reduce the burden of the application program to implement the reliability or to ensure reliability. So full functionality can only be entirely implemented at the application layer, and then there is no need for reliability from the lower layers. Right. Okay, now with that background, let's look at what are the functionalities that are provided by TCP/IP layers, the layers in the TCP/IP protocols stack. Starting from the top, the stack consists of 5 layers: the application layer, transport layer, network layer, and data link layer. The application layer deals with the data on the application, deals with how the data is presented to the user, user management, session management, etc. The payload from the application goes into the next layer, which is the transport layer. The transport layer provides mechanisms for multiplexing and demultiplexing of information, which means that when the applications run on different ports within the hosts, it is the transport layer that takes care of collecting data from different ports which host different applications and put it all onto a single channel. And at the receiving host, it demultiplexes the data that it receives from the layer below, the network layer, into different ports where each packet or each datagram is expected to go to, which means it is delivering it to the application running on that particular port. So end-to-end process communication is taken care of by the transport layer protocols. UDP and TCP have their own differences, and depending on which protocol we use, the functionalities of reliability or retry or flow control, congestion control, etc. are implemented. The next layer, the layer below network layer provides for finding a route between the two end hosts. So how does a datagram from the transport layer get encapsulated with the network layer information, with the IP address, quality of service parameters, etc.? And how does the layer 3 datagram find its way to the end host? That functionality is provided by the network layer. This is where the routing protocols are done. This is where routing tables are maintained, and so on. Now, the layer below, the layer 2 or the data link layer, is the one that provides for transfer of frames from one end of a single link to the other. An end-to-end path between two hosts in a network is made up of multiple links. So we saw that the transport layer takes care of forwarding a datagram from the source host to the destination host, from the source application to the destination application, source process to the destination process. The network layer takes care of forwarding the packet from the source host to the destination host, finding a route and routing the packet through that path. The data link layer helps it cross each link within that path, right? How does the system communicate in such a way that one packet goes from, or one frame goes from one end of a single link to the other? That is what is taken care of by the link layer. Examples of protocols in each of these layers are that application layer, let's say HTTP or email or SMTP. Now, email is an application. SMTP is an application layer protocol. UDP and TCP are examples of transport layer protocols. IP, V4, V6 are examples of network layer protocol. Ethernet, IEEE 802.3 is an example of data link layer 2 protocol. Now, we saw the functionalities of each of these layers, and we know that a layered architecture has its own advantages and disadvantages. The advantage is that if I want to use a TCP protocol from one vendor and an IP protocols from another vendor, an implementation from another vendor, then I'll be able to do that. So it allows for modularity. I can change each layer's implementation and plug it in with a different implementation. Whereas the disadvantage here is that there may be chances of duplication of functionality among these layers, which might lead to an impact on the performance, right? So to summarize, what we saw in this segment was we looked at the goals of Internet architecture. We saw the end-to-end argument that is relevant for Internet, and we also looked at the layered architecture of the Internet in terms of the TCP/IP protocol stack.